Welcome to another episode of the Business of AI podcast. And I'm delighted to be joined by Manish Patel, the CEO of Jiva.ai. So Manish, welcome to the podcast today.
Thank you for having me, Tim.
I'm looking forward to finding out more about Jiva.ai and the work you're doing there, because it sounds very unique and very different, your approach to AI in general. But I wonder whether you could just start off by telling us a little bit about yourself and how you end up getting into what you're doing today.
Sure, yeah. So I've taken a bit of a roundabout route to getting into AI, I guess, but I actually started off as a molecular geneticist back around the time when the Human Genome Project was finishing. So maths and computing was coming into a big way into the discipline. I was always not very good, let's say, at wet lab experiments. Nothing ever went right for me in the lab. And I was a much better programmer and much better at maths than I was at any kind of wet lab work. And so it was a natural transition to go into bioinformatics and that kind of thing. At postgrad, I did that as a master's and then went into AI machine learning kind of things in at PhD level. And then kind of stayed in that field ever since, very data heavy roles in banks and hedge funds in the interim. And went through the whole Lehman Brothers saga where the company collapsed. But my claim to fame is that the day I joined Lehman Brothers was the peak Lehman price, and it started falling from that day until right until collapse.
But correlation does not imply causation, right?
Yeah, exactly. And then I started helping health tech companies in their technology space, often doing sort of machine learning and AI type of work. And that was essentially it. I was hooked on from then on. And right up until when we started the company just before COVID, kind of how it came about was the people that are currently involved, the founders. The questions were around how do we do X? Often about medical diagnostics or automating certain things. And we kind of came to the realization that actually not only do we need some kind of super intelligent system that is generalized in the way it can work, we need it to be able to be sort of facing non-technical people, right? And that was really important, that you have domain experts like doctors or accountants or middle office staff in a bank who can use Excel, and that's basically the extent of their technical knowledge. They can't program in Python, and they don't necessarily understand what a neural network is and so on. So how do you get them to be able to use these kind of very technical products and get the best out of them? And that's how the story started. That's how we started Jiva, to be able to reach those people.
And so it's fascinating to hear your background coming from, particularly working in hedge funds. So quantitative analysis and sort of building those models there, those algorithms that are able to take in vast amounts of data. And I think that helped to spur on some of the scale of machine learning that took it. I mean, you've got the classic journey there, going from the academic science through the sort of like the financial huge models built there, and now into AI. So that's just a really fascinating journey there. But then tell us a bit more about Jiva and sort of, what did you set out to do with that, and what's its USP?
Yeah, sure. So our grand vision actually for Jiva is to create super intelligence. That's where we want to get to, just like many other AI companies. And it's the route that we, set the bar low, right? So that's what we want to do. And it's the route that we take that is actually very unique to us. So if you think about how our journey has gone, right? We were pre-LLM. And LLMs blew up the market in terms of AIs. And what we've always said is sort of natural language interfaces are a great way to interface with humans, but they're not necessarily doing all the intelligent stuff in the background that we actually wanted to do to become super intelligent. The two things that we think we need to be able to solve to be able to get to super intelligence. One is we need to get AIs, or artificial machines, to be able to plan in the same way that a human brain can. The human brain is really, really good at being creative about the planning steps of going about solving problems. I don't think we've cracked that nut yet, especially with LLMs and even when people talk about agentic planning. There's a lot that is in the training data set that goes into the planning stage of agents. So I don't think we've actually solved that particular problem yet. The second big problem to solve is what we call fusion. So this is the idea that, Tim, when you went to school, you were taught English in your English class and your brain absorbed that. And then when you went to your maths class after that, you were still taught in English, right? But you were being taught a completely different subject. And your brain is really good at meshing those two very different things together so that you can comprehend it and you can do something with it. LLMs, machine learning in general is not very good at doing that. Yeah, you train a machine. Sorry?
Very unidimensional, isn't it?
Yeah, exactly, right. So you train it to learn about something, and it can only ever, surmise about that particular thing. It can't sort of go outside of its bounds. And even if you do have something that's outside of its bounds, another model, let's say, you can't mesh those two models together. It's just not mathematically possible to do that with neural networks and transformers. So what we've come up with in Jiva, and what is our USP actually, is a way in which we can actually merge different models together. And that is actually our core technological USP. This ability to be able to stitch lots and lots of models together, which is actually more efficient to do than having a ton of new data and retraining your model on that new data, and doing that on a regular basis, as the large language model companies are doing right now. So we have a way of solving that second problem. We have a way of solving that first problem as well, but that's one that's going to take time. And that's actually why you see Jiva doing the things that it's doing in its marketing campaigns and on its website, which is effectively a zero-code AI platform. What we're actually doing is learning how humans are breaking down complex problems from a very abstract perspective, rather than thinking about how a human solves a classification problem. We think about things like, what kind of data was it, right? What kind of steps did they take to explore that data? What kind of steps did they take to try to create a model for that data from a very generic perspective, or a very general perspective? And we use that information to actually train our internal models to then understand how to break down complex problems in general. And then marrying these two things together, planning around complexity and model fusion, we hope to be able to get to a point where we can get to superintelligence.
This is fascinating stuff. So I love your approach and approaching it in a very different way. It reminds me of some of the conversations I've had around neuromorphic design. The idea that actually we want to look at how the brain operates and try and replicate that within the sort of the modeling environment of a neural network, or within a model. And I think part of the conversation there is around exactly, you say, that fusion point, that when we're learning, we're not learning just text. They just put kids in a room with lots of text firing it out at them to grow up as normal people, right? They have lots of multimodal sensory inputs and lots of different things they learn. And somehow at a neural level, all of that information is encoded across multiple neurons, which are all implicated in different pieces of information storage within the brain. But the complexity of understanding all of that is kind of way beyond where we've got to at the moment. But it sounds like that's the sort of challenge that you're trying to figure out here, right?
Yeah, exactly.
And how do you actually sort of replicate that level of compute? Because my understanding is that whilst compute is accelerating, we're still light years behind. Well, maybe that's not the right term here, but we're still a long way behind the compute levels of a neuron in terms of the compute we can actually get. So is that one of the main challenges in terms of being able to get more compute?
Yeah, so compute is obviously a big challenge, especially when you're a startup that doesn't have access to $500 million of cash to burn on GPUs, right? Like some people do. But there is a real benefit in thinking of things in a bottom-up perspective rather than a top-down perspective. So what I mean by that is, with the way we are currently doing things with transformers and neural networks, you're bringing the data to a pre-existing naive model, an architecture. You're training that thing under its architecture, and then you get a pristine model at the end that does something useful. And the way we approach this is the other way around. So we have the data, we have a framework, but we let the framework grow and twist and turn, so from a bottom-up perspective, and have the predictability be built from as an emergent behavior, rather than something that we're forcing on it to do a gradient descent in the example of neural networks. So we're taking a very different perspective on it. And yes, that might take compute to do, but what we've actually find is that you get a lot of compression in relatively small networks. So you can compress, what that means is that you can compress a lot of knowledge and a lot of generalizability in a fairly compute efficient machine. It could be several thousand nodes large, with, if you can visualize it as a asymmetric kind of graph. But computing that graph in a modern CPU is very, very trivial, right? It's just it literally it's done in milliseconds to do a computation. So once you're there, actually, it's super, super efficient. And I think this is sort of a step apart from the way we're traditionally doing it. So if you think about, let me give you an example. So we know that Google Gemini, for example, as many large language model companies, they'll spend literally hundreds of millions of dollars to optimize an enormous model that can't fit on a single GPU because it's so big. So it's spread across thousands of GPUs, across thousands of machines. And you're optimizing that massive thing. The way we are doing it from this bottom-up perspective is saying, okay, let's just take a really naive agentic. I say agentic, I don't mean agentic in the terms that people are talking about right now. I mean sort of von Neumann agentic framework. So very small levels of compute, and let that small levels of compute grow inside a single GPU. And what you get is effectively like a multi-model approach to breaking down your classification problem or whatever it might be. And what you get is that those little models that you build that can fit on a single GPU have very overlapping features, very overlapping behaviors. So actually you can imagine you have this big network of GPUs, half of them might die for whatever reason, but actually the model is still operable because there is enough redundancy in those little models between them to be able to still do the prediction that they needed to do. So it becomes a way more efficient way of doing things by having this methodology of having bottom-up approach to creating prediction, but also having this redundancy of behavior being built into the system as well. So we're very much, when we talk about model fusion, we're very much talking about this idea that you can have multiple models cooperating together, effectively fused together to get to the target prediction that you want to do in a way that is actually pretty efficient, right? And compressed in the way it actually represents knowledge that it's being trained on.
Yeah, and again, fascinating stuff. So am I right in thinking then that a lot of the architecture that we would have heard of in the existing models is based upon reinforcement learning, backpropagation, all the weights. That's a sort of classic architecture. And from
That's classic,
from the way you're explaining it, you're almost sort of saying we don't need that architecture. We're going to actually sort of start from scratch, from bottom up, and we're going to break it down into modules. And in doing so, we're going to find a whole level of new efficiency and effectiveness, because we're not starting with any pre-assumptions.
Yeah, that's exactly it. So this pre-existing reliance on, I mean, look, neural networks, transformers, and LLMs, they clearly work very, very well. There's no doubt about it, right? But the specific problem that we're trying to solve is not solvable in that regime, because you just cannot take. Let's just take transformers, LLMs as an example. If you have one LLM that was trained on one specific piece of data, and another LLM that was trained on another piece of data, you just can't get those two things to merge into a single model. You can't mathematically do that. You can probably orchestrate a fusion between them by querying this one and querying this one, and somehow merging the two together on that level. But you can't get them to cooperate very, very deeply. And that's the thing we're actually trying to solve, is to get to super intelligence. We want to be able to do it how the brain does it, which is to be able to mesh multiple knowledge bases that have independently been, quote unquote, trained on independent pieces of information and life experience, and somehow it's able to get all those things to work together. And the only way we see that happening is to say, like, just very sort of abstractly, if you think about the thing that you're trying to model, let's say it's the world in terms of LLMs. If you think of that as a kind of a circular enclosed space, that is your complex system, and you're building a model that models this small corner of that complex system, and then you're going to build another model based on some other data that is talking about another part of that complex system, and those two things are interrelated somehow, but you just don't know what that interrelation is. And this is what this process does, this model fusion process. It figures out where the overlap between those two things are, and then on that basis creates a single model that is merged and can actually compute on the inputs that each individual model was actually trained on in the first place. So effectively, you get this way of iteratively aggregating up to a much bigger model that is able to generalize across a space.
So the input training data is almost less important than the data you get as you're iterating through the process to optimize.
Yeah, exactly. Yeah, so that's why we say we're multimodal as well, because we're actually agnostic to what the actual training data was. You just need to figure out how to effectively vectorize that into the system.
So that could be, I can imagine, that could be a very specific sort of field of data. So that could be, or that could be biology. Yeah. If you wanted to create a sort of small case, but if you wanted to, presumably you could also have lots of multidisciplinary subjects putting in, and then you could build a larger kind of version of this.
Yeah, exactly. And I guess you can go even smaller if you want. So if we I'll go back to my academic research, we did this specifically within cancer simulations, right? So we had models that described how a tumor grows. We had models that described how vascularization happens inside a tumor, so how blood vessels grow. We had models about how a tumor might react to radiotherapy. So we had all these different models. We know they're all somehow related. Obviously, response to therapy is somehow related to tumor growth, which is somehow related to angiogenesis inside of a tumor. They're all interrelated. We're just trying to figure out, okay, what is the mathematical function, the computational function that defines that overlapping behavior. That's actually what we're trying to do, right? So we built, in our agent-based system, we built a facsimile of tumor growth, a facsimile of response, a facsimile of angiogenesis. And what we found was where they actually overlap in behavior you see a similar pattern of the topology of agents within that system, and that's the basis on which you can actually merge all those models together. So when I say it's bottom up, I really do mean in the complex systems kind of definition of it, bottom up. We're getting our micro agents to not really know about what the big system is actually doing or what we're trying to do. We're just getting it to self-organize into a model that actually predicts well the things that we want to do eventually. So we actually have a lot of candidates in the beginning, and then we whittle it down into a single candidate that actually works across the board. So it's an entirely new way of thinking about how you do machine learning.
Yeah. It reminds me, I studied neurophysiology a very long time ago.
Yeah.
And it reminds me of some of the research that was being done. This is back in the 90s, right? But trying to sort of find some of the functions of thought within brain neurons, and being able to sort of try and see similarities between, greater than or is part of those kind of relationships, and then seeing how those are represented in the brain. Sounds very similar to what you're doing now with machines. But is there then, is it all around the sort of the representation and the sort of creating these kind of abstract sort of relationships, symbolic? I know is another sort of area.
Yeah.
Are you operating in that sort of space?
Yeah, so it is there. And actually, the first iteration of this technology, again, going back to the academic work I was doing in cancer simulations, actually, the first iteration was where our agents, quote unquote agents, were clusters of cells or clusters of molecules and things like this. We were actually trying to relate the real world into this computational space. And that worked. We showed that actually you can do that. You can actually merge all these models together, and it does, when you actually simulate the system, it does look actually like a real system. And there's really good concordance between our in silico simulation of a tumor and what we were seeing in mice. So that's one way of doing it. And then we had this concept of a world model where you could say, well, okay, there is a cell, and that is part of a tissue, which is part of a bigger organ, and cells are made up of molecules, so you can get some semantic sort of understanding of what the different agents are. But actually, as that has evolved, we completely abstracted away from physical world relationships. So we still have a world model that describes the physical world, but when it gets to actually computing those into a multi-agent system that is doing the model fusion, the clusters of agents just represent abstract behaviors rather than actual real world physical entities. So rather than modeling a cell, there is a multi-agent system that effectively models the behavior of a cell and how it reacts under certain conditions. And that's become way more useful for the model fusion side of things, because actually what we care about in from a broad perspective is how all of those models behave and how they have that sort of behavioral overlap, right? And it's on that basis that you can actually create a much bigger simulation or a much bigger model of the thing that you're trying to do.
Yeah. All of this is absolutely sort of cutting edge sort of thinking. I wonder where you're sort of finding the industry is moving though, because I'd say it's very rare to have a conversation. Well, I mean, by your definition, right, you're one of the pioneers in this space, but the rest of the industry is sort of speaking very much still around LLM based solutions, and agentic is the solution. So what's your view of when is the industry going to kind of figure out that actually they need to move to this type of model?
Yeah, so I think there is space in the industry for both, right? And they both have their uses. And I'm always a big fan of using the right tools for the right job. So LLMs, in terms of natural language interfacing, there's nothing close to it. And I think that's that's a technology that's not going to disappear for a very long time. What I do think about LLMs, though, I mean, I don't know if you saw the ARC3 benchmarks, where not a single proprietary model or open source model got beyond a 5% pass mark on that benchmark for intelligence, where 100% is human intelligence. You know, how you and I might be able to solve a particular problem that we've not seen before. LLMs weren't even able to do 5%. And I think some people will find that surprising. But a lot of people will recognize that we've basically built AIs and agents, we're calling them AIs at the moment, on the basis that you can somehow understand the world simply by language processing.
Yeah.
Right? Language is the protocol with which you and I are communicating right now. It's not fundamentally intelligent to be able to generate language. You have to actually understand that there's a deeper thing under the hood that defines our intelligence and our consciousness. Now ask me what Jiva means, so we'll come back to that. So with LLMs, you can see for every dollar that's being spent on creating a new model, there is a diminishing returns on performance. That's already happening right now. And so there will be a plateau, I think, with LLMs. They do have their place, but I think fundamentally they are not intelligent. They are not. They do language level reasoning, but cannot reason beyond that. And that's one of the big reasons why Jan LeCun has gone off and created his new company and to use Jepa-like stuff to understand the physical world. And I think that's the right way of thinking about how we take LLMs specifically to the next step. We've just happened to take like a different approach, completely away from neural networks. But there's still definitely space for that sort of theory to evolve and become something more. But I do not think you can create super intelligent systems, let alone generalized AI, with just language. It doesn't look like that's possible to do.
And logically, that makes sense, right? Because the language is there to allow us to process information in one sort of format, almost like we could say very reductively a logical format. But if you're actually wanting to do the things that we've been talking about, or you've been talking about, the creativity, that planning, being able to bring ideas together, abstract reasoning, all those sort of things, that's going beyond just the logical structure. That creativity needs to have a lot of input and a lot of abstract learning, which, as you've been explaining, only comes from a sort of higher order. That you just don't have that in text. So
exactly. I think just to give you an example, my son, he's really creative. He's an artist, and he'll be doing a painting, and often, like when we're talking about this kind of stuff, he'll say, I've got this image in my mind's eye, but I can't explain it. He's obviously human. He's obviously intelligent, but he can't explain the emotion, the feeling, the image in his mind until he actually puts it on the canvas. And I think that epitomizes why language can't encapsulate intelligence, right? There are obviously intelligent beings who, as humans, who can't fully communicate complex ideas. That's art. Let's think about, quantum mechanics or something. People who are really deep into this science who can't articulate what they're thinking about until they put it down on paper as an equation, and even then it's not fully there. That just shows that you can't actually get everything into language, which kind of means you can't build a system that really replicates how we think about that stuff, right? How we are conscious about that stuff. So that's where I think we're missing with LLMs, and I think people should be aware that that's actually the case.
Yeah, no, that's a great picture that you painted there to extend that creative metaphor, because I think the brain, what's happening inside the brain, is so much more complex and intense in terms of the human experience and the intelligence that's going on, and language the speaking and the hearing is our IO, but it's reducing the sort of the bandwidth of that complexity into kind of like
exactly.
Kind of unidimensional sort of format, and so much is lost in that. And what we'd be talking about isn't just these sort of like the IO output; it's like getting inside of here and replicating that level of complexity. So absolutely amazing. Just to kind of zoom out a bit, I also wanted to kind of get your thoughts on the UK as a place to be building this slightly alternative model, because a lot of the development so far in large language models has come from the US. You mentioned Jan LeCun, who's obviously now kind of basing himself in France, and he's building his company out there, Super Intelligent Labs. I forget the name exactly, but so there are sort of other kind of beacons now. But do you see the UK and what you're doing as being an opportunity to create some sort of sovereign capabilities here in the UK that would challenge and be competitive with what's happening in the US?
Yeah. So as you know, look, there's been the sovereign AI fund from the government releasing £500 million worth of funding, whether that's direct funding or computing resources. I'm not sure what the breakdown is, but it's a significant amount of money. It's not an insignificant amount of money, but it is a drop in the ocean compared to what some of these other companies are actually raising. Like Jan LeCun raised $1.3 billion for his company at seed. Right? Yeah, it's insane. When you get that level of risk appetite from investors in the US, it's very hard to compete in the UK. We've got a lot of talent here. Look, we got our own sovereign solution in Jiva, using the same technology of Fusion, where you can effectively optimize LLMs 10 times faster than the incumbent ways. But it doesn't matter how good the technology is actually in this country. I think it needs to be recognized by the people that have the money, and they have to have the risk appetite to be able to pump money into those companies and just say, okay, look, if we want to win in this game, we've got to spread our bets across a number of companies and be okay with 97% of them losing. And we don't really have that risk appetite. We're really good in this country at starting companies and getting them through seed. I don't think we're very good at developing the ecosystem to get them to scale, right? And that's why we don't see as many unicorns in Britain as we do in the US or even India and China now. So if we want to keep pace with that, I think the risk appetite sort of profile from investors needs to change drastically to make that happen, and the government needs to support that. And I mean beyond just £500 million in a particular type of AI. But for sovereign, just on that final note there, that this is a real problem to solve, right? That we had an outreach campaign for insurance companies in the EU, just to see what we could sell. This is before we had our sovereign product, and I would say more than 90% of the no's were because compliance would not allow the company to use a cloud system that could potentially leak the data. So when we say sovereign, and this is why we went down this road, when we say sovereign, what we actually mean is a company completely owns the model and their data never leaks outside their four walls. And that's the really important aspect of sovereign AI that I think is going to become a really big deal this year and next year. I think that's going to be the undertone of the development efforts that we see in this country. And just seeing the winners from the Sovereign AI Fund, some really great companies there. Like I say, there's great talent in this country. If we encourage that, then I have no doubt that we'll be up there with the US and China. But that has to happen. That support has to be there. Otherwise, it's just never going to take root.
Yeah, really interesting point you're making there around sovereign data, because I think the word sovereign has come to mean many things. Often it's in terms of the international geopolitical kind of question and having control and being able to build a sort of ecosystem here in the UK. But actually, you're right. The question of data sovereignty is increasingly important. and the model or the way of working that you've been explaining for the last half an hour lends itself very well to having that sort of enterprise level sovereignty or national level sovereignty, whichever one you want to go for, because you're using your own data, you're training it from the bottom up. So I can see how that aligns very well with the ambition there. So just to kind of wrap things up, I wanted to sort of get a sense of what's happening next for Jiva. What's on the horizon that you're excited about this year?
So a couple of things that have cropped up. We have our own very unique way of doing agentic AI. We're also very open about the IP situation with Jiva. So even when you're on the SaaS product, our clients always own the IP that they generate on the platform. We never take hold of that. That always belongs to the client. Neither do we own the data that they put into the platform. And so the way we're developing our agents is fully guardrailed workflows that are able to do specific jobs, and the ability then to be able to publish that onto a marketplace for other people to use. And that's something that we're really excited to release actually yesterday. And we'll do a big marketing push around that in the coming weeks. And marrying that up with our sovereign product is something that's really important for us. So this is where we're enabling, for example, healthcare companies where data is really sensitive, or banks and hedge funds and insurance companies where either data is too sensitive or too large, for them to be able to run those Claude level or GPT level models on their own infrastructure without needing to worry about what happens when the US Cloud Act comes into play and data starts to get leaked from a US system. So those two things are on the horizon this year. So we're making a big push for that now to all of our clients, and we're getting really good feedback on both of those things. So really looking forward to what the end of the year is going to look like after having released these two product lines.
Amazing. Well, I look forward to hearing more about those as they develop, and maybe we can get you back to the webinar or get you involved in some of the events, because I know there's a lot of other members of UK.ai who are working on complementary areas who'd love to kind of, I think, partner up with what you're doing, and investors as well. But just to kind of to wrap things up there, how can we find out more and follow what Jiva are doing?
So the main things, our main outlets are LinkedIn and X, and obviously connect to me on LinkedIn. Just write me an email, go to the website. My contact details are there, and happy to have a chat about what we're doing. We'll be soon also be releasing a newsletter for all of our members, and including the people that aren't actually on the platform. Not necessarily just about Jiva, but just general purpose, kind of what is happening in the AI space, what to look out for, how can you leverage that in your business. That's really focusing on how you can become more productive essentially with AI technology. That's what we want to focus on. So watch this space, sign up to the newsletter, and there'll be a lot more things coming down the pipe this summer.
And it's Jiva.ai, isn't it, the website?
Jiva.ai, Jiva.ai, yeah.
Amazing. Well, Manish, I've really enjoyed this conversation, and it was fascinating to hear so much about how you're approaching this, and I've learned a lot around the way that you're sort of turning things upside down in a really good way. I think it's going to be incredibly successful. I think it's very unique what you're doing, and look forward to staying in touch and hearing more. But thank you very much.
Likewise, Tim. Thanks for having me today.